Okay, any questions so far? So I've only talked about high level, what's a ray tracing and how is it different than what we've been doing so far, but I haven't said anything about calculating rays or exactly how we're going to calculate it. Okay, so rays. So we've seen this picture several times because I think it's a great analogy of what's going on in graphics. We have our camera or our eye point, um, and then we're going to shoot out rays into the world from our eyes, and we're going to find out what we hit, and then wherever that ray landed, right, whatever that ray was, whichever pixel, we're going to draw that color, right? So we've been able to use this analogy on all of our graphics because this is how we have our world set up. So we're going to use this window analogy directly. Here's our viewing plane. Here's our window on our screen that we're going to have some pixels. We have a viewpoint, and we need to calculate some ray. So we have some pixel position on our screen where we want to calculate the color. And so we need to have this viewing ray that we want to calculate. So now, okay, at the very beginning of this class, remember we had a bunch of math vectors. We've been using that stuff. Ray tracing uses it even more so than does what we've been doing so far, because we have to calculate these vectors and rays in space and where are things going to go, right? Okay, so we don't need to review all of this at this point, but we're going to use that. A ray is half of a line. So we're going to store two pieces of information for a ray. Not just a vector direction, but the point at which we're starting. So we typically store this P, this point where our ray originates, and then a direction vector D. So we have to store these two things to represent a ray in space. And then the ray is a half line. So the length of this vector doesn't really matter. You could consider it normalized to 1, or you could consider it any length. It doesn't really matter. Okay, so if we want to get this ray, we know the point where our eye was. So we have P directly, and this direction vector is just Q minus P. So we just do some simple vector math, and we get a vector for this, right? And then this is the ray. So now this ray is our basic primitive in ray tracing. So in ray tracing, the answer to everything, all problems we want to solve, is going to be send a ray into space and see what it runs into. So once you get the functions written for send a ray into space and see what it runs into, then everything we want, all of our shadows, all of our reflections, all of these kinds of effects that's going to be the answer to everything. So it's only a question of which rays. So here's our initial ray, and then we'll have to see where our other rays are going to come from and which ones do we want to get to conceptually. So what about this step of intersect everything in space? Now, don't worry about all the math on this slide. It doesn't make any difference because we're not implementing it, right? You don't have to write a lab, so we don't have to care exactly. But I wanted to show you one of the reasons spheres show up for ray tracing is because it turns out that given a ray defined by a point in a direction, we can write down some fairly simple math, right? Just a few lines of math, which tell us, did this ray intersect the sphere, and what are the points where it intersected the sphere? There's going to be 2 points, right? So the math looks like this. Exactly what's in there. Okay, it doesn't make any difference. We got some dot products, and we go calculate something. So because it's pretty easy to calculate the intersection with a sphere, people put a lot of spheres in ray tracing, because if I have to go write my code, I want I'm just developing my ray tracer. I need to intersect with my scene. I want the easiest thing to intersect with. This turns out to be one of the easiest. So you write that function first, and you start out your world with spheres rather than with triangles. So this is why we see that in ray tracing often. Now, in modern ray tracing things, like the examples I was showing you from the modern Minecraft ray tracing or whatever, those worlds are built out of triangles because that's the other renderer they were using. So the modern ones do use triangles as a primitive. So what does that look like? So if I want to intersect my ray with a triangle, there's multiple ways to do it. There's, I don't know, at least a half a dozen different ways people go try to think about this. So I picked one to show you. And they have different efficiency concerns and different calculations. It depends on a bunch of details. Which one would you choose? You could consider a triangle to be the intersection of 3 half planes. And then we can write down some formulas about whether does our ray intersect with a half plane that has some, there's going to be some mathematical definition for a half plane. And then we're going to intersect all three and find out if we're on the sort of inside or outside of each of these half planes. And if I'm inside all three half planes, right, meaning some cross product tests pass, then I must be inside the triangle, and my intersection point with that plane actually falls in my triangle. Now, why did we not in the early days use these triangle tests? Like, why were ray tracers built using these sphere tests? Well, as you all know now, building a sphere, you know, I need at least 1,000 triangles to make that look even halfway good. And it's not going to be a very good sphere if I try to build it out of 10 triangles. So this is sort of this much math, and doing triangles is sort of this much math, which is about the same, except for times 10,000, right? So I have to put a lot more objects, and so things get slower. And so people started out with spheres. But anyway, I write a function for this, I write a function for this, now I can have whichever kind of objects I want in my scene, and I can check if my ray intersects them.